we both woke up this morning. I immediately texted you as soon as I saw the news.
Yeah.
Uh,
Press conference and everything.
Everything. Every NASA X Twitter account posted about this.
Yeah.
Obviously, it broke on every science blog and everything.
Yeah.
Because we've sort of had some evidence, but we wanted to make sure, and NASA felt it was good enough to now have the acting administrator of NASA, Sean Duffy, come out and do a victory lap that we might have got him.
Yeah.
We maybe got him.
That's what they say.
So let's start with the breaking news from today. I watched most of the press conference. I'd been following this particular, let's say, sample because at the time it was brought up and people were like, oh, here we go.
Yeah.
But at the same time, everyone was telling me, well, the Hillary Clinton administration said there was strong evidence for biosignatures on Mars 20 years ago. So what's actually different?
Well, this time it seems to be a little bit better than the one that was 20 years ago, but we're actually going to get back to that as part of our story. Okay. So it seems to be a landmark discovery.
Okay.
It is what they're characterizing as a potential biosignature.
Potential.
Okay? And not a full biosignature. A potential biosignature means possibilities that this was a signature of life. But in order to actually really nail it down, what we're going to need is the sample to come back to Earth.
Fair.
And then actually have lab testing with things like electron microscopes and all that other kind of stuff.
So we didn't discover the underground cities and ancient structures on Mars.
No channels, no like Martians.
Okay.
It seems to be a tantalizing sign that there might have been microbial life on Mars way back. Back when Mars looked kind of like Earth. Not Earth now, but Earth prehistoric, like right after formation. So the way the solar system formed, there was some giant gas nebula cloud that started spinning. The sun was born. There were outcroppings of small nuclei that became the planets, the rocky planets on the inside. The solar radiation kind of blew out all the lighter gases. So the lighter gases of hydrogen and helium formed the outer planets of Jupiter, Neptune, Saturn.
The gas giants.
Right? And the gas giants. So right after that, for about 1 billion years, Mars and Earth were both in the habitable zone of the sun. Okay? The reason why Mars looks so different today compared to Earth is because it's just smaller, and so it couldn't hang on to its atmosphere for long enough. And if you can't hang on to your atmosphere for long enough, then the atmospheric pressure decreases like crazy. And if the atmospheric pressure decreases, then you're no longer going to be able to sustain liquid water, right? And liquid water is something that we're pretty sure is essential for life.
Fundamental
Okay,
component.
fundamentally, we need liquid water as this kind of universal solvent that creates the kind of biochemistry that would be required for something as complex as life.
Asterisk, as we know it.
As we know it, yes. Obviously, there could be other forms. I mean, there's people talking about life on the clouds of Venus, on the clouds of Jupiter, and all sorts of
we haven't seen
random
it.
stuff. But we haven't seen it. There could be life in the methane lakes of Titan, but we haven't seen it.
There could be $1 billion buried in my backyard, but we haven't seen it.
We haven't seen it. And so as far as we can tell, we need life. We need water to create life, right? And anywhere there is liquid water on Earth, there seems to be life. Even if it's like near boiling,
There's
like near Yellowstone, there's life there, right?
Yep.
So it seems like the one criteria is liquid water.
Right.
You don't even need oxygen. You just need liquid water and some source of energy. In the case of Mars, that could have just been the sun, or like geological processes on Mars,
Right.
or like the already present compounds on Mars that are somehow, packed with energy that life can then exploit to metabolize. So that's sort of the Mars that NASA's been obsessed with for the longest time.
Right.
Okay. This primordial baby Mars that had liquid water.
Right.
We know that now from our several missions there. Actually, the Curiosity rover, which was launched in the 2010s, that had a primary mission of trying to find habitable qualities in Mars. It wasn't trying to look for signatures of life. It was just trying to see, okay, was Mars early in its heyday, was Mars somewhere that could house life? And the Curiosity rover found signs of liquid water, right? And so everyone was really excited. It's like, okay, there's liquid water. The next thing we should do is try to equip a laboratory on Mars that can run around like a rover, and also have all of the tools necessary to sort of do these chemical analyses on the spot and try to look for biosignatures. And that's where the Perseverance rover came in.
This makes sense because the idea is the sort of the flight time and flight windows from Earth to Mars are both infrequent and it takes very long.
Yeah.
And so to be able to ascertain before you spend the time and money to send something back, we want to kind of do a spot check on site.
Yeah. And honestly, like, you know, when the Mars Perseverance rover was launched, I think it was in 2020, during the first Trump administration, there was a 5-year search to figure out where to put it. Okay.
Right.
Because you only got one thing. This thing's the size of an SUV. You got one shot. JPL is worried about, okay, once we have a spot, how do we get it down there?
Jet Propulsion Lab, for those who don't know.
That's the Jet Propulsion Lab out in Pasadena, one of Caltech's little side projects. And, you know, so there were 60 different candidate sites.
Okay.
That they were trying to figure out.
Oh, they had a Mars Love Island.
Yeah. And then there was an international collaboration to try and figure out what is the best place to go.
Right.
Okay. And what they settled on was this place called the Jezero Crater. Okay. It's this giant crater. It's about 25 miles across. And we know from the Mars Reconnaissance Orbiter, which is something that just like goes around Mars, has all these like instruments for infrared, visible. From that, we can figure out composition of the soil
that's
surface. There, right? Yep. The surface chemistry.
Yes.
From that, we had figured out, okay, this is a pretty promising candidate. Also,
and I just want to, because the idea is we're looking for these ingredients that we view as necessary for being valuable to life being able to exist.
Yeah.
We have these tools to detect what's there, and then so we look for the perfect match for those two.
Exactly, yeah. And we got about 60 candidates. And then this one was really nice because it's a crater that had that we're pretty sure had like a lake. So it's like one of those crater lakes you can think of as that. And there was a river delta system that was going into it. So there's these beautiful like traces of like literally valleys and like river valleys going into this crater. So, you know, there's a lot of really nice sedimentary rock that's going to be there. And you're going to see if there's life on Mars, that's a really good place to go. Okay. So NASA JPL decided, okay, we're going to go to the Jezero Crater. They landed it there, which is a feat in itself. Right? Yeah. This is a SUV packed with like a whole building's worth of lab equipment, right? That like you're trying to drop in. The lab equipment has to be resilient to the heartache of getting off the Earth, going all the way to Mars, then doing a landing on Mars, right? And then everything working.
Everything
perfectly.
Works.
And it's still just such a testament to our engineering capabilities that we are able to do this in one shot. And like we're just like really good at it at this point, right? At this point, if like JPL fails and like it crashes, we'd be like, oh, you guys suck. Like, but you know, like it's actually insane how many failure modes there are, and none of them ever fail. Like James Webb Space Telescope, there was so many failure modes, and it just like didn't fail, because like the NASA engineers are that good, right? And other countries are like you know, they're crashing on the moon,
right. They're not even.
This is Mars, dude, with an atmosphere and stuff. Like it's crazy.
MARS. Red rocks.
Yay. Exactly. So we've been obsessed with Mars for a long time. That's been sort of our go-to place to try and find signatures of alien life, right? Even if it's microbial, we want to see that, like, you know, even in terms of life, that we're not alone.
I mean, here's the thing. If the part of the point is, if we are able to even confirm, which NASA says we're on the road to, that there is microbial life, not intelligent life, on the nearest neighbor that we have in the vastness that is the universe. that has implications in and of itself, even if it's simply microbial life.
Yeah. And even if it was something that was there only like 3 billion years ago, right? The fact that it was there, meaning that like the fact that like a planet that was habitable just had life, that's like 2 data points.
Right.
And both have life, right? I mean, even with Earth's data point, like the fact of the matter is, as soon as Earth was habitable, we have fossils dating back to like that.
Right.
Like before photosynthesis, we have fossils that say, yeah, we had life like basically as soon as the Earth cooled and we had water.
Right. And if we see that now in 2 locations.
Yeah, then it's like, okay, maybe it's actually a pretty ubiquitous phenomenon all across the universe.
In that once you get to the conditions that support life to exist, it does arise not at a low probability, but at a somewhat higher probability than we may currently sort of ascribe to the ability for life to arise.
Yeah. So it'd be a huge deal if we find like...
The point is, this is going to be a big deal.
Yeah, this is going to be a really big deal. And this is only half the story because obviously... however much we pack onto the Perseverance rover, it's not a lab on Earth, right? We can't put a scanning tunneling microscope up there, okay? That's even JPL guys will be like, guys, come on.
Right. We can't.
It's literally easier to go and get the stuff back.
Right.
So it's like, okay, we're making this calculation. Like, why don't we just go and get it and then just do it here? Right.
We'll wait a little longer to get it back.
Yeah. So this is the Jezero Crater.
Yes.
Perseverance was parked right on the outskirts, did a little bit of traversing around there, and then it went down this valley, down this river valley towards the crater. It went to the spot called the Bright Angel Formation, which is right in the Nare Valley. Okay, it's this like river valley that goes into the crater. Okay, and right over there is something that's really nice because you've got this sedimentary rock on the western edge of this crater, okay? And because it's a dry river valley, you're going to have potentially signs of stuff that lived in that water, right? And it's going to leave its markings in the rock, okay? Now, the best thing to do would be to just search for organic compounds.
Okay.
Right? That would be amazing.
Right.
Like just carbon.
Right.
Like we find glucose, we're like, okay. Right. We got glucose.
We got it.
Okay. The problem with finding organic compounds on Mars is it's really hard. One is because it's got no atmosphere and very little magnetic field, there's going to be a lot of radiation from the sun. Right. And that radiation from the sun over the past 3 billion years is just going to completely wreck these organic compounds, right? On top of that, you've got these things called perchlorates, which are chemicals that are highly corrosive. So they're going to react with organic chemistry, and you're not going to go see like amino acids like in abundance. You might see them in trace amounts, but you're not going to find amazing signatures like that.
The idea is the environment, because of the atmospheric dissipation, basically will have destroyed any active evidence of these organic compounds.
Yeah, exactly. So what you want to do is you want to look for inorganic compounds that have signatures of being made by organic chemistry. Okay? And so that's what this story is. Okay? This story is focusing on two classes of compounds, iron phosphates and iron sulfides. So that's iron with phosphate, which is like an SO4, or just an S. Or you can have iron and sulfur, which is the SO4, or you can have iron phosphate. Okay, and phosphorus and sulfur, phosphorus specifically, very much something that is associated with life on Earth. Okay. So finding these things is very, very nice, and that's what they found. They found these iron phosphates and iron sulfides in the rock at this Bright Angel Formation. Okay. And the way that they found these is very conspicuous. Okay. It's very weird. It's not like part of the rock itself. Okay. What they found was, so that you've got this like substrate of rock, which is this mud clay. Okay. It's got a lot of iron. And then you have these like little, they call them poppy seeds and leopard spots. Okay. They're like little tiny like beads of stuff.
I get if for all the New Yorkers, a poppy seed bagel is heresy when you get your bacon, egg, and cheese if you put on a bagel. But like it would be like looking at a bagel with these little speckles.
Exactly. Yeah, it'll be like looking at, except now it's like this clay
subsurface,
rock,
right?
Yeah, and then you've got these like speckles, right?
Yep.
And these speckles have these particular minerals that are very exciting to us. Okay. And the other thing that they found was that these speckles have these minerals, right, of iron sulfide and iron phosphate, and the only way that these things could have really happened is through something called a redox reaction.
Okay.
If you know from, this is basic chemistry, you have this thing called the oxidation reduction process. Okay, these reactions are basically ways to transfer electrons from one thing to another, and so you reduce it by taking in electrons, right? Usually it involves oxygen, which is called oxidation, but it doesn't always have to. It's really just a transfer of electrons, and we know that organic chemistry does this really well. Okay, and what they found was, like, in the underlying clay,
yes,
they could actually see carbon. Okay, so there was carbon there.
Okay.
And the gradient of carbon was coinciding with how much of this stuff you were seeing. Okay, do you see what I'm saying? So now it's getting exciting. It's like there's a gradient of carbon, which means maybe there was more life on this side than on this side. And so, and the density of this
stuff
of this iron phosphate, which is very on Earth associated with life, is tracking.
It's correlated to the gradient,
of the underlying carbon.
Right?
So now it's like, okay, this is pretty nice.
There's like sort of like two data points that are correlating very strongly that we associate with like
organic chemistry.
Right.
And so the idea is you have the starting material, which is this oxidized mudstone, right, which is rich in iron 3, which is an ion of iron. That means that 3 electrons are missing. And then what you do is you have organic carbon, and then that acts like a electron donor to this whole process.
Okay.
And then you have the iron 3 and the SO4, which is an ion that's also found in these inorganic compounds. And then that gets converted into iron 2 and just sulfide, which is just the sulfur atom. So the oxygen goes away. That chemistry is very, very organic-y. Like that chemistry is very life adjacent, if I may say.
If I may say.
Right? So that's the whole point. Everyone's like really excited about this. And one of the impressive things is that we can do all of this on Mars, right? All of this toolkit is on that SUV,
right?
The Mars Perseverance rover,
right?
Which is crazy. It's got this one instrument called PIXL, PIXL, for Planetary Instrument for X-ray Lithochemistry. Basically, it's a way to find the chemical makeup of rocks using an X-ray. They've got a little beam of X-rays that goes in, figures out what comes out. So they've got a detector, and then that tells you
what's in it.
Yeah, what's in it. And then they also have this thing called SHERLOC.
Oh, yes.
Which is scanning habitable environments with Raman and luminescence for organics and chemicals. I think they started with the acronym, and they're like, okay, how do we make
it fit?
They do this all the time. It's so funny.
Because I don't think chemicals it's SHERLOC without a K.
It's a SHERLOC with a C. But the SHERLOC is it does Raman spectroscopy, and it's basically a carbon detector in some sense. So they use the carbon detector to find like carbon on the substrate, and then they used the PIXL instrument to do X-rays on these little tiny poppy seeds and leopard spots to find that, okay, it's iron and sulfur and phosphorus.
And the thing is, I want to just reiterate, there are smart people who thought about this on the front end and had a plan in order to be able to what is the methodology by which you even like ascertain that life was there or not there, etc. Very okay.
Yeah, it's really cool that like they could fit all of this on this giant SUV, pack it into the top of a rocket, have it survive lift off, have it survive landing on Mars,
right?
And then now it's like actually giving us all this crazy data,
right?
And this data is like a year old, so they've been going through it because obviously they know this is like a big deal,
right. I remember, I believe Administrator Duffy, as part of his speech in the press conference today, made an emphasis on this point. He's like, we found it last year and we sent it all over the world because we wanted to be sure. And everyone looked at it and everyone checked it. And they got back to us and they were like, you might be right.
Well, so to that point, whenever something like this comes out, this is a big deal, right? Deal. The great things about Nature is that they make their peer review process completely public.
Yeah, Nature, the publication,
yeah.
not Nature.
Not Nature, the Springer publication that's been around, that has published all the big papers over the past 100 years.
Yes.
Very recently, they didn't used to do this all the time, but very recently they've made their entire peer review process public. So after something gets published, you can go to the website and you can go to the peer review file and see what the reviewer said. And that's incredible. It's pretty cool because, science should be open.
Yes.
And just like every grad student knows, there's always one reviewer. Okay. For me it was reviewer 1. For these guys, it's also reviewer number 1.
Of course.
Okay, because they're anonymous.
Yeah.
So if you're anonymous, you can just start saying the most heinous, out of pocket things about the work. And this guy did not hold back. Reviewer 2 and reviewer 3 were pretty nice. They were like, you should include some of these sources. You should maybe word things differently. Reviewer 1 was straight up like, this needs to be rejected. He said that multiple times in his first review. And he's like, the language is bad. First of all, okay, so...
First of all...
He was like, first of all, the title. He goes after the title. He's like, I can't believe you put biosignatures on the title. You look now, the title of the paper does not have biosignatures.
So reviewer 1 won that battle.
Reviewer 1 won that battle because they were like, okay, fine, we'll take out biosignatures out of the title, because he's like, this is only, you can't say that the null hypothesis, which is, that this is of abiotic origin, which it totally could be, right? This chemistry could have formed. We don't know what the chemistry was like 3.5 billion years ago on Mars, right? So it's totally possible that this chemistry could have formed abiotically, right? And so that was his first qualm. His second qualm was about, they have this analysis where they're looking at using the PIXL instrument. They're looking at the composition of these nodules and things like that. And he's like, well, you don't have any clean data, right? Because it's like you have like iron and sulfur and you're claiming that these are the things that are in it, but there's also all sorts of other stuff, right? And you can look at the rebuttals that the authors put back. And so the authors put back the rebuttal being like, no, the beam of the instrument is as big as the nodules, if not bigger. Right. So I can't focus harder than I already have. Right. This thing is on. It's not like I can remove a lens and put another one in. Right. Okay. Right. So it's like, this is the best data you're gonna get. Okay. So that one's fine. And it also, he was also like, the language, I can't believe you're calling it poppy seeds and leopard spots. You should be calling it by the scientific terminology, because otherwise people are going to get confused. And so they took that out and they started referring to these things by their scientific thing, which is authigenic nodules and reaction fronts. Okay. But they also, in their rebuttal, they're like, people do this all the time. We've heard of Scooby-Doo spots, right? Like people, it's not like it's something that we made up. Right. Like it's just a nomenclature. Right. Okay. His main qualm was basically like, you guys are hyping yourselves up way too much. Okay. Like, I can't believe you're saying it's a biosignature. And then he brings up what happened in 1996. Okay. With McKay and the paper in Science. Yes. Okay. So this is an incredible story because 1980s, a team finds a meteorite in Antarctica. Okay. In the ice in Antarctica.
That's where the aliens are.
That's what the aliens are. Turns out this guy definitely thought so too. McKay, right? And his colleagues. So this meteorite is discovered in Antarctica. Yes. And then because it's on Earth, we can now actually put it under a scanning tunneling microscope and things like that. And we can start looking, and there's these really weird bacteria looking things. Okay. It looks like one of those rod bacterias on this meteorite and things like that. And so lo and behold, he's like, this is life, right? It looked like life. Honestly, you look at the photos, I'd be like, oh, that's a bacteria in a scanning tunneling microscope. If you told me that it was from a Mars meteorite, I'd be like, okay. I don't know anymore, right? Because if you tell me it's from Mars meteorite, the burden of proof has suddenly gone up to here.
Right.
Okay. If it's just a rock on Earth, then yeah, there's bacteria on it.
Mm-hmm.
So he publishes this thing in Science. It's a huge deal. Okay. Bill Clinton gets in the White House lawn.
Right.
And calls a press conference.
Yes.
And he's like, I did not have but he was like, we found life on Mars and it's great. That's my best Bill Clinton impression. Good. The only thing I can do really is the Monica Lewinsky thing, but I'm trying to. But anyways, so it turns out that probably not right. Just not enough evidence to say that this thing is something from Mars. But it became a huge part of the zeitgeist at the time, because Bill Clinton was also announcing the Human Genome Project. There were all these big wins for American science, and this was going to be one of them. Dan Brown, the author of Angels and Demons, he wrote a book. Yeah, he wrote a book called Deception Point, where it's a great book, and it's the main crux of the story is that somebody finds fossilized aliens in like an iceberg. Right. So it becomes like this huge pop culture thing. And what this reviewer one is saying, he's like, you guys are repeating the mistakes of the past, right? Because the field of astrobiology has already been hurt by this sort of fake hype. And you guys are, quote, the new data set is, quote, much weaker and much less detailed than even what that guy put out in 1996.
Those are fighting words.
Dude, this guy was relentless.
Dude, that's fighting words.
Yeah, so reviewer 2 and reviewer 3, like, reasonable comments. Reviewer 1 is just going ham. Basically, several times he's telling Nature not to publish.
Right.
Okay?
Right.
The authors come back and they say, okay, fine, we refined the language. We're not saying we never said it's biosignature. We said it's potential biosignature, which is something that even NASA agrees and the greater astrobiology community agrees is what this thing should be called, because certainly it is a potential biosignature. This is something, phosphate and sulfur in iron next to organic compounds, certainly something that requires further investigation, and that's what a potential biosignature is. Well, I just thought I was reading the review and it was just like almost personal.
This is great.
Yeah.
And so we are still in a place, because now that we have the understanding of what are we actually talking about, because a lot of times with these stories of anything related to biosignatures, life off Earth, the news headlines, number one, don't map onto the words in the paper that they cover. Because they're going for clicks. And biosignature is like an amorphous word to 99.9% of everyday people. What does that even mean? But this was actually helpful, because now, in this case, specifically to this research path, we understand what we're trying to say or look for when we say potential biosignature.
Yeah, it's a potential biosignature. It requires further scrutiny.
And
further lab results.
And
so actually what the Perseverance rover did and what it's capable of doing is actually saving samples. So it took a sample out of this guy, saved it. And then, in the future, if we get our funding back, we're going to send stuff there.
Pick up the sample.
Pick it up and then take it back to Earth.
So I think what this means is, if we want confirmation that our neighbor, the red planet, remember we're code red today, does in fact not just have potential evidence of biosignatures, but it is in fact biosignatures, we got to go get it. And in order to go get it, we have to fund the programs that are getting us so close to better understanding our place in the universe, and that what we think of as life is potentially way more abundant than we thought. But we have to spend the money.
We got to spend the money. And the thing is, I think like SpaceX and Blue Origin are in talks, or at least they were before the massive spending cuts. They were in talks to like try to design a mission to do exactly this. Right?
This is a good point. Private aerospace has risen in its power and its efficacy over the last, let's say, 10, 15 years. Particularly driven by SpaceX, with Blue Origin as a close second. Where do they get some, if not a large portion of their capital to even do those things.
Yeah.
Where do they shoot their stuff off from? All government funded.
Yeah.
All government funded.
Yeah. What are they shooting? It's government funded stuff. Yeah. It's not all Starlink satellites.
When we send astronauts up, right?
Yeah.
The government is paying SpaceX to build a capsule to be able to put humans in.
Yeah, I mean, and it's following what the American model for innovation has been for the longest
100%.
time, which is the government spends the money to do all the hard work,
right?
And then once they figured out all of the little details, now the private sector can come in and be like, oh, okay, I can now do that, and I can do it cheap, and I can do it well, right? That's the same thing that happened with silicon transistors, right? The government gave a blank check during the Apollo missions to a small company in Silicon Valley that used to be a bunch of apple orchards and orange groves, right? A small company, blank check. I need this size of computer in something like this, and I need it to not overheat. And blank check, do it. I just need it. Okay, we got to beat the Russians. They do it. They're like, well, now I can make computers.
Yes.
Out comes Fairchild Semiconductor, out comes Intel, out comes all of the Silicon Valley tech.
Yes.
Right? So it's a model that's followed, but again, it needs, like, you still need the government to have that money and have that funding to jumpstart these things.
100%. This is not to exclude the idea or the fact that the private industry can and has, particularly in aerospace, pushed the boundaries of innovation.
100%.
But these are not mutually exclusive ideas.
Yeah.
Like, yes, both things can be true.
Yeah.
And both things are true, particularly as we talk about these deeper space missions in particular, where there is no commercial value.
No.
For a private aerospace company for these more, again, fundamental discovery points.
Yeah, exactly. I mean, maybe you're trying to colonize Mars, but that's like several hundred years away.
Yeah, and not in our lifetime.
Right?
And,
yeah.
And unless we figure out the longevity issue, which we talked about in last episode, we won't be around for that.
Yeah, I won't be around for that.